My name is Anne Broadbent. I'm a professor in the Department of Mathematics and Statistics at the University of Ottawa. I would like to introduce my team: Rabib Islam, Sebastien Lord, Suparto Potter, and Danielle Pozzoli. Quantum mechanics describes the way that particles behave at the atomic level. And physics tells us that at that level, our intuition completely breaks down. That is, that there are quantum phenomena that are really interesting to study and look at, and that's what we're doing in our research group. Conventional computers are used in our everyday lives, and the basic unit of information for these computers is the bit. It's a discrete state. It's either 0 or 1. In contrast to this, in quantum computers, the basic level of information is called the qubit, and this is in a continuum of states between 0 and 1. Actually, it's in both states potentially at the same time. This is called a superposition. So what our research team is doing, we're looking at quantum phenomena and trying to take advantage of these for communication and information processing tasks. One of the really cool things of quantum mechanics is that it predicts something called the no-cloning theorem. According to this theorem, it's impossible to make two perfect copies in general of an unknown quantum state. At first, this sounds really useless and annoying because our everyday intuition about copying information doesn't hold. For instance, it would not be possible to make a backup copy of quantum information. But where some people see a challenge, we see a new opportunity. So we're trying to take advantage of the no-cloning theorem and other quantum phenomena to have more secure crypto systems, which will allow for more secure communication and more secure information processing. Quantum computers are computers that process information at the quantum level. They're known to give access to incredible computational power and to solve some problems efficiently by quantum methods, and these solutions are more efficient than any conventional computer could ever hope to achieve. So one of the quantum algorithms that is known is the factoring algorithm, i.e., given a large number, how could we decompose it into its prime factors? And the consequences of this quantum algorithm are huge because most of current security that we use over the internet is based on the assumption that factoring numbers is difficult. So in the advent of quantum computers, and many experts believe that it's just a matter of time, we will have to completely retool our information infrastructure in order to be secure against these quantum attacks. Thus, we urgently need to find a solution to the information security question in the presence of quantum computers. And one solution, which already exists and it's already even implemented, is quantum key distribution. And this is a method to securely distribute messages among parties on a network using quantum information as the information carrier. Don't get me wrong, mathematics is very much involved here. In fact, there are some profound mathematical results that are used in the security analysis of the techniques. However, the underlying assumption here would be a physical assumption, the correctness of quantum mechanics, versus, in the case of conventional computing, a computational assumption, the hardness of factoring. Another question that our team is looking at is the question of delegating quantum computations. Here we imagine a cloud quantum computing service that has a quantum computer that is accessible remotely. And the question is, could users remotely access this service while maintaining privacy of their data and of their algorithms? And we've come up with many solutions, including solutions to verify the correctness of the quantum computation. We're also looking at problems of unclonable encryption, certified deletion, and many other consequences of the no-cloning theorem. Given the steady progress in building quantum computers, we're hoping that our research will contribute to a more secure digital society.